Hello everyone, my name is Zhenhuan Yang. I am going to present our work, FairnessAware Differentially Private Collaborative Filtering. This is a joint work with Yingqiang Ge, Congze Su, Dingxian Wang, Xiaoting Zhao, and Yiming Yin. We will first introduce the motivation of this work. On a high level, this work belongs to the recent trend of trustworthy learning. In particular, we consider automatic decision-making in recommendation systems. And for the social impacts, we will focus on the privacy and the fairness. For the traditional collaborative filtering, it has been witnessed in the literature that it runs the risk of privacy leakage by using users' interactions history. Typical adversarial attacks include membership inference attack and sensitive attribute inference attack. To protect users' privacy, one of the state-of-the-art technique is differential privacy. This is a statistical rigorous privacy mechanism designed for quantitative analysis. A randomized algorithm is called differentially private if the learned distributions with or without a certain user in the dataset are similar. So any adversarial attacker cannot identify the user's information. The parameter epsilon is the privacy budget to quantify the protection level, and the parameter delta is the privacy tolerance of failure probability. On the right-hand side, it is the most popular algorithm in this field, namely differentially private SGD or DPSGD. Compared to the common gradient-based algorithms, DPSGD requires two additional steps after the backpropagation and before the parameter update. They are L2 norm gradient clipping and Gaussian noise addition. However, we have empirically observed for the first time these two additional steps will result in worse, unfair treatment in collaborative filtering, which is our second focus of trustworthiness. But before discussing this, we will introduce group fairness between the active user and the inactive user. The activeness is defined based on the number of interactions between the user and the set of all items. The top 10% of users are considered as active, while the rest are considered as inactive. Due to the fundamental idea of collaborative filtering, users with lower activity levels are more likely to receive lower NDCG, or so to speak, unsatisfactory recommendations, even when differential privacy is not introduced. To make our statement more rigorous, we introduce the user group fairness measure, which is defined by the absolute difference between the group level utility metrics between Group A and Group B. In our case, the utility metric is given by NDCG. The trade-off we observed is when DPSGD is introduced, the user group fairness measure decreased by 15 to 20% among Amazon review datasets. This is also called the pool become pooler phenomenon, or the Matthew effect. To address both the user privacy and the user fairness issues in collaborative filtering, we introduce a two-stage learning framework. The first part is differentially private training. In this part, we employ Bayesian personalized ranking laws as our objective to learn a parameterized scoring function f. It is worth mentioning that we apply DPSGD steps to user gradient and the item gradient separately in order to minimize the need of Gaussian noises, while maintaining the same privacy budget. In the second stage, we conduct non-parameterized post-processing to address fairness. We put the user group fairness measure as a constraint in the following linear programming problem. The design of the problem is to select a subset of recommendation lists from the top capital K list given by F, while the maximum sign-up score, or so to speak, ranking utility, is preserved. Now, our two-stage learning framework, DP-FAIR, is summarized on the right-hand side. We employ the Octopus module to conduct DPSGD steps. We also employ Gurubi solver to solve the LP problem. We conduct experiments on Amazon review datasets, and here it is one example. We consider non-deep and deep models in matrix factorization. We also consider rank-aware metric and non-aware metrics. From left to right, the privacy budget epsilon gets tighter. However, our algorithm always outperforms vanilla SGD in the total column, which is the overall utility measure. Furthermore, our algorithm also provides smaller user group fairness gap. This is due to improvement on the inactive user group utility with some sacrifice from active users. In summary, DP-FAIR is more robust in both utility and fairness against DPSGD. Thank you for listening.